Afternoon session. And our first talk today is going to be by Reinaldo Marques on online particle path functional approximation for large data sets.
Thanks for the invitation. This is a joint work with Guy Stovk. Part of this work was done in my PhD. So the idea here, we're going to a little bit talk about particle methods. I'm going to give a brief review of what's going on here. If you see here around particle methods, basically I'm going to focus on 3 points here. First, the method is convenient to approximate sequence of target distribution. Here, the problem here, the target distribution here, it's an increased space. So typically the problem that you can see in time where you have, for instance, the posterior distribution time 1, 1 to 1, 2, 1 to n, and so on. Or maybe you can see this problem use particle methods in a kind of integration problems. For instance, we want to estimate z, the z function here, this integration. If you're familiar with the notation of Feynman-Kac measure, you can see here as the transition kernel here, the potential function, maybe going to appear here as a likelihood. And then you need to integrate, at least approximate this integral. Or even more, you can see this problem build online stochastic algorithm, where you try to at least fix the computational complex, here in the order of the number of samples. So that's the main task of particle method. Basically, you are focused on solving on these 3 problems together, or focus one of the problem. Just for review here, where you are. If you remember here, important sample, then one derivation of important sample is sequential Monte Carlo. It started here in 93, and then you have a lot of methods here. Here, most of the main papers around the sequential Monte Carlo. And also you have MCMC, and here, down here, you have here the combination of MCMC and particle methods. So the basic is important sample, and sequential Monte Carlo is a sequential version of important sample with more structure. And you have some papers here combine SMC and MCMC. You can see this problem in general state space model. I'm going to just review here and introduce my notation. If you remember here, you have the model, observation model, have YT, give the whole path to depend only in some latent variable here, xt. And the xt, you have some transition model, maybe Markov model, first order. And you have a static parameter, you can put some prior there. It's very useful, and it's very normal notation. And here you can see as a graphical model, the evolution here. So most of case x is latent, you would like to understand the evolution of xt, given the data you have. An example here, if you see state space model, here is one paper about asset location. We have return here, and then you have the evolution here for the return. You can put some Gaussian here. If 8t is deterministic, you can run this by Kalman filter as usual. So, in the state space model, given theta, if theta is null, the inference relies on the filter distribution or this MILF distribution. So here's t in 1 to t, or maybe you have the whole data, you want to understand the posterior distribution xt. Then you call filter and you call smoothing. However, the hard work will be here in the sample for the joy distribution when theta is unknown. So maybe you can do You can try to do this dynamic, or maybe you can do this static, as you can see in the famous paper by Andreu, PMCMC or SMC square, Chopin et al. So here is the hard test. You try to do this dynamic where you try to build some algorithm with fixed computational, and you try to sample simultaneous from the latent state and the parameter. You can remember this can be high dimensional because you can accumulate a lot of data. Theta also can be quite a lot of parameters that you don't know. And then give you the data, sequential Bayesian inference, you can see the posterior distribution here, pi of x given the data that you have. Then you can split your posterior distribution here. And then to simplify the notation, you are interested in this pi of x 1 to t. And also you can write the marginal likelihood in terms of integration of 1 to t that you don't know. Unfortunately, you know that few cases you can compute this analytically. This is an tractor problem. Most of the problem cannot solve this integral here. And also your posterior intractable. So, sequential Monte Carlo method, aka methods. The idea is approximate pxt 1 to t, use the proper weight sample, where you have the sample and you have the weights. Typically, you have some proposal, and you have a posterior here. Then you propagate by simulating some proposal here, depending on xt. Maybe you can use the data here, and then you compute your WT, weights for your sample in time t. Then you can see here, you can compute, use the previous 8, then you propagate your particle and save your weights. And also, for free, you can obtain the model evidence estimate by doing this calculation here. Very simple, traditional and particle methods. So if you remember in statistics, you have this problem here. As t increases, you have so-called degeneration problem. You can focus on this proposition here. If you have pi t, v1, v2, and key v1, v2, two probability density and support of pi subset of q. And then you note that the variance of this ratio here is greater than the variance of this ratio here. In practice, it implies, you can see that as t increase, the variance of the weights is going to increase. So one cosmetical solution for that is a practical solution is to add resample step. As you can see here in the algorithm, the simple way is to see the particle method is at time t1, you sample for your proposal, then you calculate your weights, then for time t1, time 2 and 3 and so on, you have the x, you propagate the x, might use your data, and then you compute and normalize your weights. And then for some criteria here, you can use a resample to control the variance of the weights. So here, what's going to be important for this talk is the definition here I'm called recursive path functional. Well, let's see ST be a sequence of measured functions defined on xt and rt. So if there is one function t and xt minus 1 multiplied by xt and rd such that you can write this a combination your function and xt minus 1 xt, I'm calling here recursive path functional. It's just to remember that you try to see how you combine your samples that you have. For instance, in a simple case here, you can combine it in an additive way. A very simple example is like one sample correlation here, where you can see here, you can use xt here, 1 to t minus 1, and add this term here to compute the lag sample 1 correlation here, x1 to t. So the problem is, as you see in the literature, maybe you can focus on this paper here, and the Biomath 2011, the variance of the ST using the particle method increase at least quadratic in time. So if you have a lot of data points, the variance of your estimate is going to increase. So in practice, you cannot use this particle method to approximate this functional here. So in order to try to solve this problem, at least minimize this problem, let's see one simple idea here where you can divide your time t1 to t, so your whole path that you have, and subinterval of length L. Then you assume t and t multiplied by L. Then you can write your functional as a sum of each block that you have. So for instance here, if you see here, it's a bit clear here, but if you see here, you have points here, and you have blocks. I divide the whole time series here, and blocks. And then you can add. Suppose that you can create some mechanism that you can compute the functional for each block, then I'm going to add. Let's focus here in specific case where you have this additive structure. So my idea here that simulation for pi of x1 to t, given the data, can be obtained for the simulation from pi s1, s2, sn. Then I can compute here each block. So this idea is based actually in two approximations. First approximation that I have, I can tell you this block is dependence. I'm creating dependence in between blocks, among blocks. That's the first approximation. And the second approximation, I say each block, the information that you have for one functional in these blocks, you're not dependent of the whole data, only for leg k here. So I'm trying to compute this posterior here for the whole path based in blocks, and these blocks are computed based in these two approximations. So it's a bit clear here in this the algorithm, but I'm trying to modify the original particle filter. You cannot see here, but basically what I have to do is you have one local functional, or try to update the local, additive local functional, and here, down here I have the global. After I update my local, then I'm going to update my global functional. What I'm trying to do here, if you're back here, maybe I will quite quickly here in this, try to explain here, when I try to stop the number of resampling that I have, the number of times that I resample each block. After I calculate the functional in this block, and then I wait for the leg k, then I stop. That's done. Then I continue to run the algorithm. So of course you can create more extension. This size you can update the functional. It's not necessary to be additive. And also you can extend this idea when theta is a null. What you have to do is write these proper weights if joint for xt, for x, 1 to t, and theta. And you do some manipulation here, you see that the weights are proportional, the previous weights, and this ratio here is appear here. The posterior distribution for theta, and the proposal. In case of you have this posterior, you can write this posterior, then you cancel here. But if you know this, you have to simulate this theta, give the whole path. This is the problem. If you have to simulate the whole path, the estimation of this path, maybe your sufficient statistics, should be appropriate. If you have degenerate here, the distribution of theta, also you can see some degeneration in the distribution of theta. Of course, y is the data. So then you can also extend this for simulate joint distribution, x and theta. And the simulation of this is based on split, of course, joint the blocks, the x and theta, and then you split and see, then you can sample this theta, give the functional for each box. Also, you can update the algorithm. And you see here, you sample theta from your posterior distribution, given st minus 1 here. Then you have to compute this. This is the global functional. The global functional is updated using the local functional here for each block. So then in my algorithm here, I only include this line here that you have to compute this functional for each block. Yeah, of course, you have to resample as an option in the method. In this method, of course, I introduced one tuning parameter, the size of the block. So I have to specify L, SK as well, if you use the leg. And then if you remember, decrease L means like more blocks that you create, more error you create. However, but increase L, you back in degenerate. So maybe L should be increased as a functional number particle. If you are able to simulate with a lot of sample, then you reduce your degeneration. And now, of course, it's possible to consider adaptive block split that you can run and calculate the number of the size of the block together. Theoretical result, if you see here works of the Swedish guy and the French guy, they have similar mathematical foundation for expectation maximization MLE, but not for the Bayesian setting. So I'm trying to do some calculation here. I still working this, but I try to see the distribution provided by particle methods, the distribution provided for the first approximation, for the second approximation. I'm trying to create some open bound here. Let's see some experiment here. Simulation use a Gaussian state space model. If you know, I know the true posterior because it's a Gaussian. The observation model is Gaussian. The latent model is Gaussian. You can run by Kalman filter. If you see here green, the green is the Kalman filter here, or the green is the particle filter, the ordinary particle filter. The blue you can see as a true. The Kalman is moving, and then you have the red here and the light blue. You try to follow the Kalman is moving here. You can see here the particle field, like around here you can see the whole the great degeneration here, and also create the posterior here quite wrong compared to the true posterior. And also you can see I'm running here a lot of points, and I still follow the Kalman is moving here. Then I have three choice of B and K, B equal K here, and 500, 100, two choices here. And also I compute the distance here. I'm trying to evaluate the distance between the true here by Kalman filter again, and also provided by the algorithm here, and they compute here the maximum of the distance. And you see here the green here. In this case here, fix this the static parameter. And you see here the blocking control the maximum of distance between this two distribution, and you see the ordinary method, the distance, the maximum distance increase in time. In this extreme case here, where you can see huge degeneration, when I increase the correlation here, and then you can see the particle method here doing quite bad, and you see increase here also in the blocking, but much less than compared to the particle filtering. Just some comments. I introduced some block independence approximation here. It's promised to avoid degeneration in online estimates. You can run a lot of data points. Block length needs to be specified. In our experiment here, the block strategy outperformed the guide, the ordinary particle filtering. Stable with the block size. And adaptive approach for specify the block length also is possible. Suggests welcome. And of course, you can also design better propose how you move from one block to another block. And also you provide some R library here. It's called dynamic latent linear model. The idea you can sample when the data is any distribution, and X is a linear here, and Gaussian. Then we try to combine ISC and the spec SMC utils, and then I have output calma, ordinary sequential Monte Carlo, how localization parameter estimation, blocking with simultaneous parameter in the online version. Thank you very much.
Any questions?
Hi, have you tried to implement your algorithm with particle MCMC methods like?
Particle PMCMC?
Yeah, or you only check the paths that were generated?
No, because the PMC is offline, so I was not interested in this moment to do this.
Okay, thank you.
Are the blocks evaluated independently? They can be parallelized in R, for instance?
Sorry.
You can do parallel computation. They can do independent evaluation in the blocks.
If I can create
You can do independent evaluation in the blocks.
If
Can you parallelize? Yeah.
Maybe you can, but maybe it's not a good idea, because if you see here, if you see idea here, that you try to understand XT given your whole information. So if you try to create this algorithm independent, maybe you're going to lose some information here. So because this is the original idea of particle methods, is you try to do the sequential, and also you try to learn from the past, at least from your neighbors, right? So that's why I wrote here in the end, better proposal, you can apply this if you try to think about what's the best way to connect this one block for another block.
Any other questions? Okay, let's thank the speaker again.